When you go to buy MOSFETs, you'll see that they're usually rated for crazy high amps in the datasheet, but that only pans out if you have good heat dissipation, because as soon as the MOSFET gets really hot, then it will stop working and break. So one thing you can do is put it on an extra large copper pad. I don't even have a heatsink on this MOSFET because the copper pad is dissipating, wicking away a lot of the heat from the tab. So at this setup here, I have the load connected between the positive from the battery and the drain, and then when the MOSFET turns on, it connects the drain to the source to ground to complete the circuit. Since this is a 12-volt battery, I can connect the gate of the MOSFET directly to the supply rail through a 330 ohm resistor. That way 12 volts will be plenty enough to put the MOSFET into full saturation. My DC load is in constant current mode, set to 20 amps, so it will adjust the resistance until 20 amps are being pulled. Alright, I'm going to go ahead and start this by pressing the button, and that will connect power to the MOSFET. You can watch immediately the temperature beginning to rise on the MOSFET. That's 100 Fahrenheit, so maybe about 40 or 50 Celsius. And the temperature climb is still going up, but it's kind of slowing down. 120 degrees. That's about what your T is. It's comfortably warm. And that's 20 amps, so it's dissipating, it's controlling a load of about 200 watts. And if we take a look real quick at the voltage drop, this is the MOSFET drop across VDS, and you take the amperage and multiply it by the voltage, you get the power. So about just about 1 watt of power dissipated at the MOSFET. And the datasheet for this MOSFET says it can handle up to about 40 watts-ish. And of course that's if you have proper heat dissipation, or proper heat flow away from the MOSFET. Well, it's pretty fun to stress test MOSFETs in this way. You can see there's all kinds of big loads you'd be able to control with 20 amps.